Now that we have covered counters and gauges, it's time to dive into histograms. Histograms are built on top of counters. There are some gauges as well, I'll show you, but mainly counters. And I have made a change in this project. I have added a histogram. What I have added is app request latency seconds. And whenever a request count is incremented, I add a request latency, which is sampled from a uniform distribution between 0.005 and 15. Basically, this is also a simulated metric like request count. This project is running for quite some time on Docker Compose, and the reason why I did that is so that we have some data. And let's go to the UI, Prometheus UI, and look into all the metrics that we have captured. So I'm going to filter it by the metric for histogram, and if you look at this, you will see there are 4 odd metrics. There could be a couple more like min and max, but what we care about is this bucket. This is where the histogram is stored. So let's dive into that. So I'm gonna query this. So let's go here and open bucket, and you see that there are a lot of series here. Let's filter it by a single instance app1. So for app1 we have 15 series, which is expected, and they are different because the LE value is different for them. And LE stands for less than equal to. It's a convention for buckets, but each series is actually a counter. To prove that point, let's go to the graph, and you notice these values are incrementing. So each series is actually a counter. And another thing to notice here is, since this is less than equal to, the way you would read it is less than equal to 0.005, the counter is 0. Less than equal to 0.01 is equal to 1. Values that are less than equal to 0.025 is 5, and so on and so forth. And that is the reason why it keeps on incrementing here. So basically, values less than equal to positive infinity covers everything, and then under 10 is a small portion of it. 7.5 under 7.5 is a smaller portion of it, and when I say under, just assume that it's less than equal to, because that's what this operation is, or that's what this label is. Now you can see the same thing here. The topmost one is actually LE plus infinity, and that is the biggest value, and the next one should be 10, and the following one should be 7.5. So that's what is happening here. That's how histogram is stored in Prometheus, and honestly, this is the most efficient way to store histograms. And whenever you do math on top of it, and the most useful one I found is doing histogram quantile, which pretty much gives us the percentile value. And they're all approximation, but they're pretty good approximation of percentiles. Now, when you add series to Prometheus, it takes more space. So one optimization that is possible with histograms is, we have created 15 odd series here or 15 odd buckets here for this histogram. But it is possible to define your own bucket, and you can define maybe like 10 buckets or 9 buckets or how many ever you want, and then the number of series will reduce. And that would also mean the resolution of the data will also reduce, but up to your use case, right? Sometimes you care about certain buckets, and you can encode those buckets into your metric, and then the number of series will reduce. Now let's see what we can do with this data, right? Now that we have this information about histograms, the very useful thing that we could do here is calculating percentiles. I usually look at 50th percentile because that's a fair approximation of how my requests are doing on an average. Not really average, but it's a fair approximation of average. So I'll do this. I'll do rate over last 5 minutes is basically this value, And then what I could do is I can call this function histogram quantile, pass the quantile here. So let's say 50th percentile. And if I run this, I get the 50th percentile. And you see that the LE is dropped here. And the 50th percentile is 7 seconds. It's a uniform distribution between 0.005 and 15 seconds. So this being 7.6 makes a lot of sense, right? Now let's look into like 65th percentile. It's 9.62, uniform distribution. Let's look at 30 percentile. It's 4.5, uniform distribution. Now the thing is, it is possible that a lot of values will be missing, right? Like we don't have a 4.5 in our data set. What we do have is we have 2.5 and we have 5.0. So what histogram quantile does is it does linear interpolation between these two. So let's say 2.5 is 520 and 5.0 is 1033. So it will do a linear interpolation from 520 to 1033, and it will figure out where does, let's say, 4.5 lands, and that gives that allows histogram quantile to figure out where does 35 percentile live, where does 65 percentile live, and so on and so forth. So that's how histograms work. It might seem a little intimidating at first, but it's actually quite simple once you understand what data is stored here.